Chapter 10 Astronomy. The sky is wondrous on a clear, cold, moonless night far from city lights. We marvel at the majestic sea of stars, thousands of stars, navigated by a half-dozen planets and the occasional brief meteor. Scientists are no different in their sense of awe and wonder, and they turn to the stars in their search for answers to questions about the meaning of it all. To our unaided eyes, all the stars look like brilliant points of light, some a little brighter and others fainter, some colored with a hint of red or blue. But when we focus our telescopes skyward, we see many different kinds of stars. Some are hot and dense, burning their fuel at an incredible rate. Others are cool, consuming fuel much more slowly. We see stars in their infancy and stars growing old. And once in a great while, we catch a glimpse of a star in its final cataclysmic hours, racked by a massive, fatal explosion. All this variety of stars tells a story. Stars experience a cycle of birth and death. The life of any star is a constant battle against the force of gravity, which tries to pull the star in on itself. Against this unremitting force, stars deploy a variety of countervailing strategies. Some of these strategies allow stars to stave off collapse temporarily, and some strategies allow them to stave it off forever. But nothing can protect the largest stars from eventual collapse into a black hole, the ultimate victory of gravity over matter. The birth of stars. All stars begin as diffuse clouds of dust in deep space. Somewhere in the cloud is a place where matter has gathered by chance more thickly than elsewhere, and the force of gravity exerted by the clump pulls in neighboring materials. This makes the clump more massive and increases its gravitational attraction, so even more material is pulled in. It's not hard to guess the outcome of this process. The cloud starts to collapse around the original concentration of matter. As the concentration progresses, the pressure and temperature at the center increases. First, electrons are torn off their parent atoms, creating a plasma. Then, as the contraction continues, the nuclei in the plasma start moving faster and faster, until, at last, nuclei approaching each other are moving so fast that they can overcome the electrical repulsion that exists between their protons. The nuclei come together, and nuclear fusion begins. The nuclear fires ignite. Energy from fusion pours out from the core, setting up a pressure in the surrounding gas that balances the inward pull of gravity. When the energy reaches the outer layers, it moves off into space in the form of electromagnetic radiation, and the stabilized cloud begins to shine. A star has been born. The primary fuel for the fusion reaction is hydrogen. Two protons, the nuclei of hydrogen atoms, come together to form deuterium, an isotope of hydrogen consisting of one proton and one neutron, and some other particles. Subsequent collisions of the deuterium with other protons eventually produce helium-4, a nucleus consisting of two protons and two neutrons. In symbolic form, the nuclear reaction can be written as 4 protons yields helium plus energy plus leftover particles. As in nuclear reactions, the conversion of mass, in this case some of the mass of the 4 initial protons, supplies the energy. While the star is contracting and stabilizing itself, some interesting events are taking place out in its periphery. The original cloud will, in general, have some small rotation. As the contraction starts, the rotation speed increases. The cloud is like an ice skater who, when she pulls her arms in while spinning, spins faster. If nothing counters it, contraction will increase the spin until the star is torn apart. There are 2 ways for the nascent star to avoid this fate. It can split into 2, forming a double star system, or it can form planets. In both cases, the spin is transferred from the body of the star to the revolution of the stars or planets around each other. Most stars seem to take the double star route. At least 2/3 of those you see in the sky are multiple star systems. The search for planetary systems around other stars has revealed several stars with multiple planets, and astronomers are searching for a system like our own. Stellar lifetimes. The appetite of stars for hydrogen is truly prodigious. The Sun, for example, consumes some 700 million tons each second, with about 5 million tons being converted into energy, primarily in the form of gamma rays. Yet so large is our star that it has burned its hydrogen at this rate for 4.6 billion years, and will continue to do so for more than 5 billion years before running out of fuel. How long will a star live? That, of course, depends on how much hydrogen it has and how fast it is consumed. Oddly enough, the larger a star is, the shorter its lifetime. The reason for this seeming paradox is simple. The bigger a star is, the greater is the gravitational force trying to make it collapse, and the more hydrogen has to be burned to keep the star stable. The Sun, a quite ordinary star, has enough fuel to keep gravity at bay for 10 billion years. But a star 30 times as massive as the Sun must burn its fuel in such a profligate way that it will shine for only a few million years. A star much smaller than the Sun, on the other hand, will live for tens of billions of years, longer than the age of the universe. The star just pokes along, doling out miserly bits of energy into space as it husbands its hydrogen throughout a long and frugal life. The death of stars. Profligate or miserly, every star must eventually burn up all of its hydrogen, filling the core with helium ash. When the hydrogen is gone, the outward force generated by the nuclear reactions disappears, and gravity resumes its inevitable inward march. The inner parts of the star start to contract and warm up. For a star like the Sun, the interior heating temporarily produces more energy, as hydrogen burns just outside the core, and the outer regions of the star are pushed farther outward, creating what astronomers call a red giant. 5 billion years from now, the body of the Sun will extend out past the present orbits of Mercury and Venus and will scorch Earth's lifeless surface. The core continues to contract even as the outer layers puff up, and soon the core becomes so hot that helium, the ash of the hydrogen fire, itself starts to fuse. In a series of reactions, 3 helium nuclei come together to form nuclei of carbon. Once the helium is consumed, a process that may take only a few minutes in a star like the Sun, the collapse starts again in earnest. The bloated outer layers are blown off, while the inner region continues to contract. There is no more fuel to burn, so something else has to stop the collapse. That something else, for the Sun and stars like it, is related to the behavior of electrons. Electrons in the star cannot overlap. They need elbow room. Only so many can be crammed together in a given volume. When the core has collapsed down to the size of the Earth, its electrons will have reached the point where they cannot be further compressed, and the star will be stabilized forever, with gravity pushing in and the electrons pushing out. A star held up by pressure from its electrons is called a white dwarf. It generates no internal energy, having used up all its fuel, but continues to glow for a long time as it cools off. Currently, theorists believe that stars with masses up to 8 times that of the Sun will end up as white dwarfs. Made almost entirely of carbon nuclei, such a star is truly, as our childhood rhyme told us, like a diamond in the sky. If the star is very massive, however, its death is much more spectacular. It burns through its hydrogen quickly. Then, after a short collapse, it starts burning helium to make carbon. When the helium is exhausted and the inevitable collapse starts again, the temperatures at the center of the star get so high that even the carbon starts to fuse. This pattern continues, the ashes of each fire serving as fuel for the next, as the star desperately tries to stave off the inevitable. In the final stages of nuclear burning, iron starts to be produced. Iron is the ultimate nuclear ash. It is impossible to get energy from iron by allowing it to fuse with another nucleus, and it is impossible to get energy from it by fission. As the star's core clogs up with iron, there is no way for the star to generate more energy. Again, the collapse starts, but this time the force exerted by the electrons is not enough to overcome gravity. Electrons are forced inside the protons in the core, neutrons are produced, and the core shrinks quickly to a sphere of neutrons, a neutron star, about 10 miles across. The force of gravity and the pressure of neutrons against each other balance, and, providing the force of gravity is not too strong, the core stabilizes. Supernovae and their consequences. When the core collapse occurs, the outer parts of the star find that the rug has been pulled out from under them. They start to fall inward, meet the rebounding neutron core and a flood of neutrinos created in nuclear reactions, and the star literally tears itself apart. For the space of about half an hour, shock waves crisscross the stellar carcass, creating temperatures in which all chemical elements up to uranium and plutonium are synthesized in a wild free-for-all, then blown into space. For a brief few days, the star can emit more energy than an entire galaxy. This event is a supernova, the most spectacular stellar cataclysm known. When the dust has cleared in a supernova, the end product may be a neutron star or a black hole. We don't know enough to predict which with certainty. On February 23, 1987, a star exploded into a visible supernova in a neighboring region of our galaxy, giving astronomers a ring-sized seat during the spectacle and, not incidentally, giving them a chance to verify their theories of how stars live and die. The theories came through with flying colors. When the fireworks of a supernova are over, all that's left of the original large star is a neutron core, a sphere of solid neutrons about 10 miles across. The neutron star is usually rotating very fast, typically turning on its axis 30 to 50 times a second, because the collapse speeds up the original slow rotation of the star. Remember the ice skater. The star's original magnetic field has also been concentrated by the collapse, and a field many trillion times that at the Earth's surface exists on the neutron star. Electrons spiraling in toward the north and south magnetic poles of the rotating star give off energy, mostly in the form of radio waves. This radiation moves out into space in a narrow beam focused at the pole of the star. You can think of it as being something like the rotating beam of a lighthouse. As the beam sweeps by us, we see a pulse of radio waves, then darkness, then another pulse. When these signals were first seen in the radio sky, they were called LGMs, for little green men, because they looked like coded signals. Now we realize that they result from rotating neutron stars, which astronomers call pulsars. More than 1,000 pulsars have been discovered, and thousands more undoubtedly wait to be found. If the star is very massive, then even the force exerted by the neutrons will not be enough to overcome gravity, and the collapse will continue down to a black hole. Black holes represent the ultimate triumph of gravity, the ultimate defeat of the star. Our picture of the life of stars, then, is that early in the history of the universe, large stars formed, lived their brief life, and became supernovae. In the last moments of their existence, these stars synthesized all the known chemical elements, then returned them to space. There, these elements in turn are incorporated into new generations of stars as the concentration of heavy elements increases throughout the universe. All elements heavier than helium, including the iron in your blood and the calcium in your bones, are made in stars. We are all of us made of star stuff.